Hi everyone, welcome back to this R tutorial video on simple statistics for the book Climate Mathematics, Theory and Applications. This video corresponds to section 2.2.7, and some of the topics we'll be covering involve dealing with data stored inside of data frames, both continuous and categorical or discrete random variables, and also reporting descriptive statistics and graphically viewing those descriptive statistics with distributions. So let's get started. One of the first packages that we need to go over is the DPLYR package. Now the DPLYR package is a wonderful way of working with data frames. So with one of the libraries, we have to install it on our computer, and I'm assuming that this is your first time working with the DPLYR package. So let's use the install.packages function and put in quotes DPLYR. I already have it installed on mine, but of course if you don't have it installed, you need to run that. And then once you see it run and successfully download onto your system, then you can access the DPLYR library. So this is a required library, and it's going to help us when dealing with data stored in data frames. For the majority of this video, we're going to be using the mtcars dataset. And this is a preloaded dataset in R, so in order to access it, we use the data function. So I type in the data function, the name of the dataset I want to access, and here I see in my global environment, mtcars is there. Let's look at mtcars structure. So I want to see what types of variables there are, how many variables there are, how many observations there are. The str function is a wonderful tool for viewing metadata about the data frame that you're accessing. And here all of our variables are numeric, even some where I do see a lot of repeated values. Now there's a difference between being a numeric variable and a factor variable, which we will discuss very soon. And just to verify that mtcars is a data frame, we'll use the class function, and it returns data frame. And so we can all review the difference between a matrix and a data frame. A data frame contains different types of classes as variables, while a matrix can only contain one type of class. So you can have a matrix of characters, or you can have a matrix of numerics. You can have a data frame containing characters and numerics, or you can just have a data frame of all numerics. A data frame is a more generalized version of a matrix because it can contain different types of variable classes. So notice that all of the variables in the mtcars data frame are quantitative, even the number of cylinders in a car. Now there's no such thing as having 5.5 cylinders in a car or 2.5 cylinders in a car. You're going to have a whole number. So does this make sense for cylinders, which is under the variable sil, to have repeated values of 6, 4, and 8 and to still be treated as a numeric variable? It doesn't. So let's change this current numeric variable into a factor variable. And the way we do that is we can coerce it from a numeric to a factor class. And we specify, remember we can access variables from data frame using the $sign. I should be more specific. Specifying the data frame, the $sign allows us to access the variable, and then we just type in the variable name. The as.factor function coerces this entire variable from a numeric to a factor variable. And since we just coerced it, we can see the levels contained within the factor variable, and those levels are 4, 6, and 8. So we've coerced this from a numeric class to a factor class. And I also noticed that gear was inappropriately labeled a numeric variable. Let's do the same for that. So we coerce it from numeric to factor, and here we have, instead of 3, 4, and 5 being considered numeric quantitative measurements, now it's a factor variable like the number of cylinders in a car. So those variables were examples of dummy variables. They look numeric, they sound numeric, but in reality they aren't numeric. They're just dummy variables. If I were to plot these on a distribution or a continuous distribution, it would give me no value whatsoever because I just see stacked repeated values. That's why they're called dummy variables. But with these types of variables, as we set them to factors, we can examine subpopulations or different groupings of things using these variables as reference markers. And we'll start to see that. So we can look at overall distributions, we can look at particular distributions. Let's say for cars with 4 or 6 cylinders, that's a subpopulation of our entire data set. So dummy variables are helpful when we want to assess subpopulations. Now that we sorted out some of the issues associated with the data frame, let's review descriptive statistics, specifically measures of center and measures of spread. So descriptive statistics, they include things like the mean, the median, the mode. For spread, they include standard deviation, range, variance, and quantiles. So what are they? All descriptive statistics do is we observe characteristics from a population. So we're interested about a population, but we can only observe them from a sample. We're not running tests on the population, we're not putting claims up about the population, we're merely observing it. So one major branch of descriptive statistics include measures of center. A prominent measures of center, which we'll cover first, is the median. And the median is also denoted as the 50th percentile, the second quartile, or in plain jargon, it is the middle of ordered observations. And when I say ordered observations, I'm talking about observations that have been ordered in ascending or descending order. It doesn't matter, as long as there is an order and it's the middlemost observation. So for this one, we're going to analyze the quantitative continuous variable of miles per gallon. And I want to find the measure of center and the median, so I want to determine the median gas mileage of the entire data frame. Simple command, the median function will do it. I specify the data set, use the $sign to access the variable, miles per gallon, and I run that. And I see here in my output that 19.2 miles per gallon is the median. And let's say that you aren't satisfied. How do we do it manually? Well, we can order the miles per gallon values in ascending or descending order using DPLYR's arrange function. And then there's another command in the DPLYR package called the summarize function. And we can find the second or the 50th percentile in the quantile function to derive the median. So in essence, we sort it in ascending or descending order, and then we determine the median using the quantile function. DPLYR is best used when you employ a pipeline approach, and that's what the percent greater than percent symbol really is it's a pipeline. So I specify my dataset, empty cars, and I use this pipeline right here, and that allows me, instead of typing out empty cars $MPG, I'm in the empty cars dataset. I want to arrange these variables in ascending, or these observations in ascending order for miles per gallon. And then after I sort those observations in ascending order, I want to find the median. How do I find the median? I use the quantile function. The variable of choice, miles per gallon, and probability. So you can specify multiple probabilities, but since the median is in the 50th, or is the 50th percentile value, we just specify probability equals 0.5. So let's take the median of this using the pipeline approach with DPLYR. And here we see, in our output, just using the median function, we get 19.2 miles per gallon. Doing it manually through DPLYR, again 19.2 miles per gallon, they match up. So now that we covered the median, and just a bit of information about that, the median is resistant to outlying observations, while the mean is not. Specifically the arithmetic mean. So it's also called the average of all observations. You sum up the observations, you divide by how many observations there are. A simple concept, but it's hugely important in statistics. A simple function, just like taking the median, you can take the mean of any variable by specifying the mean function. And this is using the $sign approach to access the variable within the empty cars dataset. So let's take the mean of that. So our median and mean, relatively close together. I haven't measured spread yet, so I can't say if this is a skewed or a non-symmetric distribution, but we'll get to that later. Similarly, using DPLYR, I can approach it using the pipeline method, specify my data frame, then I can use a pipeline, and I can use the summarize function to calculate the mean. And remember, when I use the pipeline approach, I don't have to put a $sign next to every variable and the data frame, because I'm already in the data frame when I specify it at the top of the pipeline. So using DPLYR, I see that the mean function and the DPLYR approach give me the exact same results. Now we're moving on to discuss the mode of a distribution. There is no function in base R that can provide you with a mode, so we're going to have to create our own function. It's a good review, and actually some of the previous videos discussed creating functions in more depth, so please feel free to brush up on them if you feel a little rusty making functions in R. But the mode is generalized as the peak of a distribution. In calculus, we refer to this peak of a distribution as a maximum, and there's an entire field in mathematics for optimization, which can be performed to determine minimums and maximums of some type of function. Let's create a distribution for the overall miles per gallon, and we're going to specify lower and upper limits with it. And when I say lower and upper limits, the smallest value and the largest value contained within the MT-CARS dataset for miles per gallon. So instead of using the MT-CARS $sign approach, I can also use the with function. When I use the with function, I specify my data frame, and then every variable within that data frame comes with it. So I don't have to say MT-CARS $sign miles per gallon, since I specified it in the beginning portion of the with function. And I want to plot the density curve of miles per gallon, and I'm going to leave off the title for now. So let me expand my plot size in RStudio, because sometimes the plot function can get messy if you have too small of a plot window, so let's make that large enough. And here we have a density curve, the estimated density curve. And there were a lot of options I left off, especially if you know a lot about statistics. Things like bandwidth, the type of kernel can all affect the way that a density plot is formed, but we just use the base default functions. And here we have, for all 32 observations in the dataset, a density plot that shows us with one mode. The largest peak of it is right here at what looks to be about 18 or 19 miles per gallon. Let's put a title on this plot. I can use the title function. And our title is Overall Distribution of Miles per Gallon. Let's determine the minimum miles per gallon. Again, use the with function, specify my data set, and I want to use the min function to find the minimum, the smallest observation for miles per gallon. That's stored in min miles per gallon in the global environment, and that is 10.4 miles per gallon. The maximum miles per gallon, same concept, but I use the max function. The maximum is 33.9 miles per gallon. AB line. AB line is a function that can plot a horizontal, a vertical, or any type of linear line. A straight line, a sloped line, a steep line, a flat line, a horizontal, a vertical line. It deals with lines. When I specify the V equals option, it says that I want a vertical line. So I want a vertical line at the value 10.4 miles per gallon. That's going to signify our lowest boundary. I also want another vertical line at our largest observation, 33.9 miles per gallon, and that'll signify our upper boundary. So taking into account all of this, here I have my two vertical lines representing my lower and upper boundaries. They're in red. They have a line width, LWD, of 3. And that is the overall density distribution using the default settings to calculate that density distribution for miles per gallon. And going back to our discussion about the mode, let's use the density values to find the maximum of the distribution. So we plotted the density curve, but we had to find the density first and then plot those values in that function. Now we're not going to plot the values, but I want to store them. I want to collect them in an object called density vals. And I just leave off the plot function, and I just keep the density function. And here I see that it is a list of 7 objects. And those 7 objects contain a vector of 512 observations, actually 2 vectors of 512 observations, x being our original data, y being our density function. And so I want to extract those 2 vectors and bind them together in a matrix. So let's do just that. Since density vals is a list of 7 different objects, we have to access it appropriately. So it's not like a data frame, but since we're dealing with a list, we have to use proper list notation to extract those vectors. I use the cbind function to form a 512 by 2 matrix, so 512 rows, 2 columns. And I extract the first object from the list, specified by double bracket notation, and the second value from our list density vals. And when I bind those 2 vectors together, I get a matrix of 512 observations and 2 rows. Now let's calculate the max density value. We're going to use the max function. I'll be examining the second column, so I want to find the maximum in this column. And obviously it's going to increase and increase and increase, and then, like any good maximum in calculus, once we reach that where it stops increasing, where the slope equals 0, that's how we know we've hit a maximum. If we're increasing with our slope, we hit 0, and then we start decreasing with our slope. So we use the max function to determine that, and I store it in max dense, which just means max density. And now I'm going to use the which function to locate exactly where, in terms of our x values, our miles per gallon values, that max density is located. So I use the which function to locate that. And then, to finally find our mode, I use the row value given to me by locate, and I plug that into our original density vals matrix. And then printing that value out. Here I have 17.90862 miles per gallon. So that is our mode. Let's include the mode inside of our distribution. Again, we'll use AB line. It'll be a vertical line. And in this case, we're going to color that vertical line blue. Instead of me typing this number out, I'm going to make it simple and try to automate wherever possible. So if people plug in a different variable or different data frame than what I do, at least the mode variable can change. It's not going to be a constant number, but it can change. So let's include that. It will be a different line type, same line width, blue color. Let's put that on. And here we have it. The mode of our kernel distribution. Beautiful. The slope increases as it approaches the mode from the left. It hits a 0 slope, and then it starts decreasing as we continue down the density curve towards positive infinity. So instead of typing that all out and having to specify it multiple times, let's make a simple to call function for finding the mode of any variable, since base R doesn't have it. I will call this function mode, and it will be a univariate function of one vector or one variable. Again, I'm just going to pretty much copy and paste the code that I had up here, store it in a function, and I'm going to return a value of the mode. So let's create that function. And now let's check our function to see if it works. Using the with function, I can access my variable without having to use the $sign. And I call the mode function, plug in the variable I want it to calculate the mode of, and here we have it. So using our custom defined mode function, we came out with the exact same results as above, and it is correct. In this video, we went over the DPLYR package, and we covered different measures of center, graphically and descriptively, including the mean, median, and mode. In the next video, We'll cover different measures of spread and introduce you to various measures, including the range, variance, standard deviation, and how to interpret quantiles and percentiles. I hope to see you in the next video, and have a great day. Thank you.